Hello, this is Ted Baldry with EasyPower. I want to welcome everyone to the EasyPower webinar series. Today we have a presentation being done by Yvonne Grobelar, although I probably pronounced that wrong. Because Yvonne is out of the country, is from South Africa, as we typically do when people are presenting from out of the country, we pre-record it. Yvonne is still going to be online answering questions live as we do the presentation. If you'll look in your GoToWebinar control panel, there's a place where you can, there's a little questions pane, and if you click the little button, you can pop out the questions pane and see those a little easier than just leaving it in there. I'm going to start out as we normally do. Jim is normally doing this, but he's out of town today, so I'm hosting this presentation today. We're going to start out with poll questions like we normally do, and the first question, let me launch it. If you could answer this question. What best describes your interest in this webinar? There's no obligation, you don't need to do these, but this just helps us to get a better understanding of the interest of the audience. Okay, I'll show the results for that. All right, let's move to the next one. Have you ever seen lightning damage to a wind turbine? Thank you for your responses on these. These are some questions that Yvonne submitted for us to put in the poll questions. All right, looks like we have a pretty high response rate. Let me show those. All right, and the final poll question is, are you familiar with IEC 61400-24? As I mentioned earlier, if you during the webinar, if you post questions, Yvonne will be able to see those and respond in there as well. All right, let me share the results of that one. Looks like most people have not heard of it prior to this webinar. All right, I'll go ahead and start this video. And again, thank you for participating in the EasyPower webinar program, and I hope you enjoy this. At the end, we'll open up some time for Yvonne at the end to answer questions, either live with his mic if he's able to, or you can still submit questions after the end.
Hello everyone, and welcome to this week's webinar. Thank you again for joining. This week's webinar is regarding lightning protection and earthing for wind turbines. Now, this forms an essential part of wind farm design. Now, we've seen in the news lately, on social media, multiple cases of damage to wind turbines caused by lightning. And I read a lot of the comments and suggestions going around on social media, and it was quite clear that there is a lot of confusion on why this happens, how to prevent it, and to ensure that you can provide a very long uptime and prevent unforeseen maintenance to wind turbines. And the aim of this webinar today is to provide just that. So my aim for the webinar today is that you understand things such as lightning, how lightning is formed, how it strikes to wind turbines or terminates onto wind turbines, things like risk assessment and What's the main or the key differences between doing a risk assessment for something like a wind turbine as opposed to a normal building, for example. The biggest focus will be placed on measuring and detecting lightning on wind turbines and how this data becomes useful to prevent unplanned downtime to wind turbines or catastrophic damage to blades or lightning receptors and so on. So just to introduce myself, my name is Ivan Grobelaar. I work as the Technical Director for DEN's subsidiary in South Africa. Now DEN is a global leader when it comes to lightning protection, surge protection, earthing, and recently engineering as well. So we are a specialist lightning protection company that was founded in 1910 in Germany. It's a German-based company with a global representation through various subsidiaries all over the world. In South Africa, we have a well-established engineering team, and this team conducts lightning risk assessments, lightning designs, earth designs on a daily basis, and it forms a key part of our daily work. I do list my email address there. You are more than welcome to reach out to me if you ever have any questions or you require assistance. I will try to help as best as I possibly can, or I will be able to possibly direct you to someone that can help. Also possibly in your country. Now, just to look at the agenda for the webinar today, I firstly think it's very important to discuss lightning itself and to give you background on how lightning is formed and what different types of lightning strikes can occur and why are some of them more dangerous than others and which ones would be more applicable to something like a wind turbine. After we understand that, we can move on to showing some examples of lightning damage to wind turbines. These could be minor, it could be major catastrophic damages, and again, this is based on how you implement your lightning detection or avoidance system. From that, we will discuss lightning risk assessment. Now, this is a very, very important part of the whole webinar, is that there is a standard for doing lightning risk assessment. It's an IEC standard called 62305 Part 2. Now, this is the main standard for doing risk assessments, but it's focused on structures and buildings. This is not always applicable to something, for example, like a PV plant or special cases such as wind turbines. So the IEC has written a standard specifically for calculating risk for wind turbines, and we will have a look at this and discuss the key differences between 62305 and the 61400, which is for wind turbines, and how it highlights the risk much better. And then we will discuss how we can mitigate catastrophic damages to turbines by means of using lightning detection, which is a relatively new concept, but it's been streamlined very well to the technology that we have available today. From that, we will have basic views on earth designs of wind turbines. This is actually quite standard, and also then discuss a very brief slide on simulations for step and touch on wind turbines. But there's nothing special for this in a wind farm or a wind turbine scenario. It is still a standard earth design when it comes to 50 Hertz step and touch, and nothing special there, but I will give you just a brief overview on what to expect, and then we will conclude the webinar. Now, firstly, as I mentioned, we have to understand lightning. So we have to just discuss and give you a background on how lightning is formed and how do we have different types of lightning strikes and why do we have different types of lightning strikes. Now, firstly, there are many ways that a thunderstorm cloud or a charged cloud can be formed. The method that I explain here forms the basis of what is the most common method, but there are other methods as well. Now, firstly, thunderstorms come into existence when it's a very hot day and the ground level is heated up by the sun itself. With this, surrounding air and air masses are also heated up, and if these air masses contain sufficient moisture, they will rise up and they can transport various different things such as moisture and so on up into the air and form clouds or charged positive or charged clouds that have already been formed. As these hot layers of hot air starts to rise, it creates these large updraft channels within the clouds. Now these upward drafts can have high speeds up to 100 kilometers per hour. With this movement, large cumulonimbus clouds are being formed. And with all this movement within the clouds, water droplets and water particles and ice particles and things like that will cause friction amongst each other due to the movement, and this will then start to charge the cloud. Now, a cloud is always charged in such a way that the positive charge will collect in the upper portion of the cloud and the negative charge will collect in the bottom or the lower portion of the cloud. Now, it can happen that the charge will try to neutralize itself within the cloud, flashing between positive and negative within the cloud, and this is known as a cloud-to-cloud flash. So that's when we see this flashing in between the clouds, but it wasn't an actual lightning strike to Earth. This is generally not a very big risk to electrical systems. However, it can cause an induced effect, an induced current and voltage in overhead lines and things like that, possibly also on wind turbines, but this is not the main reason for lightning or lightning damage. What could also happen is that you have a lightning strike from cloud to earth or cloud to ground. Now this is what we know as a lightning strike. Now what's quite interesting is that a cloud can, or a flash from cloud to ground could either happen downward, so from the cloud itself downward, or it can actually flash from ground level up into the clouds. It could be either direction. Now, knowing this and how a cloud is being charged, we understand that it could be upward or downward. We can now move on to looking at the 4 different types of cloud to ground lightning strikes. Now, the first one is when we have positive charge collection on ground level. The downward leader, so the lightning strike would be called a downward leader. The downward leader would originate from the negative portion of the cloud, with the bottom portion of the cloud, and it would flash to Earth with a negative polarity or negatively charged. Now, this is known as a negative downward flash. This is the most common of all lightning strikes, and it makes up about 90% of all lightning strikes globally. These also generally carry the lower amounts of lightning current and they have lower peak values. There is a Seagrave paper that discusses that there was a study done, and it discusses a collection of lightning strikes globally, and they found that this makes up the most common and about 90%. The Seagrave paper is also mentioned in the IEC 62305 Part 1 standard. What could also happen is that the ground is negatively charged and the leader would originate from the positively charged portion of the cloud and strike downward from the positively charged portion, having a positive polarity, and then terminate onto ground. So these are both downward flashes. They could be either negatively or positively charged. And on the left, you can see a picture on what this typically looks like. Very familiar, as we know, with lightning striking down to Earth with all the branching. And you can generally see that that was a downward lightning strike. The other 2 types of lightning strikes are upward lightning strikes. So This could again be either negatively charged or positively charged depending on the charge on the ground level. But what's different with regards to this is that the charge actually collects on ground level. It goes to a tall structure, and from the tall structure it flashes up out of the tall structure into the clouds. Now, as I said, it's mainly on tall structures, so it would be something like a high-rise building, a telecommunication tower, or a wind turbine. These upward strikes carry very high amounts of energy, charge, and current, because all the lightning current is focused on a single point from the structure from where it flashes, and that is where we have a lot of damage. And this is typically what would cause harm to personnel inside tall structures, or would cause damage to tall structures and equipment within those structures, like a turbine blade. On the left, you can see a picture of what that typically looks like. You can see all the concentration of charge at one point as it goes up into the clouds. Now, a lightning strike has four main characteristics that we consider. Now, these four characteristics form an essential part of lightning protection design, equipment, lightning protection components, how they are tested, and each of them plays their fair role in why the standards are written the way that it is. So the first one is the peak value of lightning current. Now, the peak value of lightning current is, as it states, the highest amount of current in amps. Now, in lightning protection, we speak about kiloamps only. So it would be the Ka value of the lightning strike. Secondly, lightning is an impulse. We'll discuss that in detail now as well, but lightning is an impulse, and that impulse has a rate of rise before it reaches its peak value. Now, that steepness and that rate of rise also has an effect, a mechanical effect on equipment within a lightning protection system. So it will be responsible for mechanical force and flash over and things like that. The third one is the charge of lightning current. Okay, so lightning current carries high amounts of charge, and charge is responsible for energy conversion at a single point, so it would also be with regards to temperature rise. And then we have specific energy. Specific energy is the integral of the lightning impulse current squared, and this is responsible for heat distribution through a lightning protection system as well. Now, for the purposes of this webinar, we will focus on two main ones relating to wind turbines and wind turbine design, and that would be the peak value of lightning current as well as the charge of lightning current. If we look at the peak value of lightning current, it is important to understand that lightning is seen as an ideal current source, or an almost ideal current source. The impedance within a lightning strike is almost zero. Now, when this current enters a conductor or into a lightning protection system, there could be a voltage drop across those conductors and current carrying components within the lightning protection system. And if we do not control the massive voltage differences within a system, that could cause flashover to try and neutralize the voltage difference between the two. When the current also enters the soil, it creates a very large ground potential rise, and the ground potential rise measured in voltage can roughly be calculated by using Ohm's law, where the current coupled with the earthing resistance would give you ground potential rise voltage. As I mentioned, lightning current is an impulse, so it has a rate of rise and then it decays back to zero. Now, we speak about the 10 by 350 microsecond wave shape, where it will reach its peak value in 10 microseconds and decay to half of its value in 350 microseconds. So lightning is very different to something like power frequency, as it's not a sine wave, it is an impulse. If we look at the other characteristic, which is charge, I mentioned that charge is decisive for the energy conversion at a single point. So this is also responsible for melting, puncturing, and heating the point at where it strikes. It all comes back to the charge within the lightning current. Now here you can see some examples of different materials, and you can see the amounts of charge onto those materials, and you can see the puncturing at the material. So this charge is responsible for melting objects at the point on where it's terminated. Now, if we look at this impulse of lightning current again, the charge is the integral of this impulse, or the area under the curve. So it's the integral of the current over time, or the area under the impulse curve. That would be the charge contained within that lightning impulse. Now, understanding now that peak value of lightning current and charge is a very large contributor to damage, we can also have a look now at some examples of lightning damage to wind turbines. These first damages are smaller damages, or smaller type of damages, except for maybe the one on the right, which is quite a lot of damage to a blade. But what happens is that high amounts of charge or accumulated charge can cause damage to the turbine blades or the receptors. So we will speak about a lightning receptor in detail in a few slides as well. But a turbine blade contains what's known as a lightning receptor. And when there is a lightning strike onto a turbine blade, there's a concentration of charge at a single point. Now, if it's small amounts of charge, you can see small damages to blades, small repair work, or even to receptors. But if it's also a lot of accumulated charge, this could increase on that weak point on the blade. It would increase the damage. Now, the aim for us is to ensure that the damage to the blade is limited as much as possible. So we only have minor repairs and nothing major. It's very important to note that it's not possible to avoid lightning strikes to wind turbines. The turbine manufacturers will have a lightning protection system implemented into the blade, but there's no way to avoid the blades of getting struck. If we look at some catastrophic damages, you can see this is typically what we've seen in the news as well. Turbines catching fire due to very large amounts of charge and very high peak currents onto the blades. And it also causes further subsequent damage. So the turbine's not switched off, it's still rotating, and it causes damage to bearings and things within the nacelle. So the nacelle is the upper portion of the turbine, and that can cause a fire. Now, I mentioned that lightning protection is implemented into wind turbines during manufacturing. Now, how this lightning protection system works is that the turbine itself will have a foundation earthing system, and then that would be connected to the base of the turbine, either as a reinforced turbine with reinforcing, or a metallic base and towering system as well. And then at the top, inside the blade, you will have a lightning down conductor. There are different designs between different manufacturers. You can see this is on the outside of the blade, some of them are in the middle. But there are requirements in IEC 61400-24 on how to implement this. Now, along this down conductor, there are connections to the outside of the blade with what is known as lightning receptors. Now, these lightning receptors look like coins. They're small metallic parts that look exactly like coins along the blade itself, which is connected to this down conductor. Now, knowing that we have upward strikes on tall structures, and so on wind turbines as well, the charge content will accumulate at the base of the tower, and the current will move up the tower through the reinforced system up to the nacelle. The current will then move through this conductor in the blade and then exit the blade, as you can see here, through one of the lightning receptors, and it strikes to cloud. So all the lightning current is focused on that single receptor, and that receptor will have its limitations. So that receptor needs to be rated to a specific charge content, and if it sees more than an accumulated amount, that's when high amounts of damage occur, and that's what we'll focus on. There is, however, a very small chance that you have a downward strike onto a wind turbine. The standard does mention that it's possible, but there's nothing that they can do about it. Because the way the lightning is formed and strikes, it can strike in between receptors and still damage the blade. There's nothing that you can do to avoid that. But the majority of lightning strikes are upward, and for that you need a lightning protection system in terms of receptors and down conductors, which will then ensure that lightning current leaves the receptor through the lightning protection system and goes up to clouds. Now, the risk assessment to determine the number of events or number of strikes onto a turbine is extremely important. The aim is to calculate number of events to see how many strikes we will have onto a turbine, and then determine what type of damages we can expect. What are the number of strikes per annum, and where would the damage mostly lie? Would it be structural, electrical, and so on? And what is the risk to human life when people are inside the nacelle or inside the base portion or around the turbine as well? As I mentioned, the lighting protection standard for wind turbines has a special method in IEC 61400-24 for calculating risk onto or for lightning strikes onto wind turbines. Now, to discuss that, we have to take a step back and go to the standard 62305 part 2. And as I mentioned in the beginning, this was the first standard from IEC to calculate risk due to lightning, and it was focused on structures and buildings. This is a very comprehensive standard, and all the other industries take the majority of their calculation methods from the standard. So the 61400 standard for wind turbines was formed on the basis of 62305 part 2. Now, as I said, the aim is to calculate the number of events to a structure, or the number of strikes to a structure, and this forms the basis of any risk calculation. If we know how many times we will get struck, we can also calculate the probability that we will have damage and what would the amounts of damage be. Now, the number of events is then obviously calculated based on the lightning activity in the area, known as flash density, and the size of the collection area of the structure. So flash density is a measure of, or a measuring technique or method for lightning activity in an area, and it's measured in the number of lightning strikes per square kilometer per annum within the area. The collection area is the area that the building or the structure takes up, and we see how much this area fits into a single square kilometer to determine the number of strikes to that structure in a given year. It's also important that the structure may be surrounded by other structures of similar heights, smaller, it could be on a hilltop, it could be isolated, and that is known as a correction factor, and it adjusts the number of strikes. So the standard says if there is another structure next to me which is the same height as me, there's a 50-50 chance that either of us will get struck. So this factor becomes 0.5. So we halve the risk of getting struck between the two, or the number of strikes between the two of us. Now, this is the formula for calculating the number of direct strikes from IEC 62305 part 2. What 61400 does is it changes the lightning activity in the area. I will explain why in the next slide. And the correction factor for a wind turbine is very different than that to a structure. Typically, these structures are very tall. They are installed in areas where there are high elevations. They are subject to winter lightning, and that changes. So if we increase the correction factor and we increase the lightning flash density, or the lightning activity in the area, the number of strikes will then also obviously be increased. And that's where 61400-24 has some of the biggest differences as opposed to 62305 part 2. Now, as I mentioned, although IEC 61400-24 follows similar methods to 62305 part 2, there are fundamental adjustments made to accommodate tall structures of wind turbines. Firstly, it's stated in 61400-24 that a wind farm may increase lightning activity in the area. Now, that makes sense if you look at it from a practical perspective. If I have a collection of very tall structures, typically wind turbines nowadays are 200 meters tall. If I have a collection of a lot of tall structures within an area, I create a very well conductive path, or very good conductive path for upward lightning strikes between ground and cloud. So effectively, I decrease the air gap between soil and clouds. That means that there could be a lot of collection of charge within that area, and it's very easy for that charge to make its way to clouds. So a wind farm may increase lightning activity in the area. So after building a wind farm, you will see that there's more lightning within that area. If we then calculate risks according to the standard for buildings, there are 4 risks that we typically calculate. The one being loss of human life, dangers to human life. We could also calculate loss of service to the public. So if it's something like electricity supply, water supply, public service, we want to calculate if there's a risk that the public would be without that service. We could also calculate loss of cultural heritage in something like a church or place of worship, or a building that's more than 100 years old or contains items that are more than 100 years old. And then the last risk would be loss of economic value. So that's the risk of damaging equipment and structures and so on and so forth. You don't have to calculate all 4. You only select the ones that are applicable to your situation. In 61400-24, we calculate loss of human life, similar to 62305. But we split the risk of economic loss. So we calculate the risk of physical damage to the turbine and the risk of electrical damage to the turbine. So this is a fundamental difference between the two. There's no mention of anything like service to the public or loss of cultural heritage in this standard. Now, I mentioned that the standard also adjusts the amounts of lightning strikes or the lightning activity within the area. We mentioned that it increases it. As I briefly mentioned, lightning activity is measured as ground flash density, and it's measured in the number of lightning strikes to a square kilometer per annum. Now, this is a map from the NASA optical transient dispersion. This highlights the lightning flash density globally. So the value for ground flash density is then read off of these type of graphs. The one on the right is a map of South Africa, and the value is then just measured off of this graph. In 61400, the value is converted to what is known as strike point density. Because we said we increased the lightning activity within the area, the standard adjusts the flash density by doubling it. It's multiplied by 2, and then we have a factor for strike point density. I also mentioned that the correction factor is different. So the correction factor, again, is just looking at surrounding objects to see what are the chances of your structure getting struck as opposed to other ones within the area. Now, in 62305, we simply just look at, am I isolated? Is there something else around me that's the same height or smaller? Is there something that's much taller than I am? Or am I isolated on a hilltop or no? In 61400, it's broken up into 3 different correction factors, and they are all added together to make up one correction factor. Now, the first one is terrain complexity. I will explain that as well. But we look at, is the turbine situated on a flat or moderate area, in a hill or in a mountainous region? And it's calculated according to a ratio, which I'll show to you in the next slide. We also look at the height above sea level and the possibility of having winter lightning or lightning strikes within the winter months. Now, the correction factor for terrain complexity is calculated based on this graph or this image in IEC 61400-24, where we look at the peak value of the hilltop on where the turbine is based, if any, and then the distance away to the first or the lowest terrain. From that, we use H divided by D, and we get a ratio, and then we select the factor. Winter lightning is also given in IEC 61400-24, so you can see, again, a global view, and you select in your country based on this scale what the lightning activity in winter would be in your region, and you select that. So if we then make the adjustment between the two standards, and you look at 62305 part 2 on the left, this is the formula we mentioned earlier for the number of direct lightning strikes. If we adjust it to 61400, we then have to change flash density to strike point density, and the correction factor has to be increased to accommodate all the correction factors added together that are applicable to wind turbines. So it's increased. Now I did a comparison. If I take the same structure or the same wind turbine, which is 200 meters tall in an area with a lightning flash density of about 5, in a mountainous area with a high elevation, if I use the old method that's not adjusted, you can see the number of strikes would have been calculated as 6.8 strikes per annum. If I use the method from 61400-24, that value is increased to 67 or 68 strikes per annum to a wind turbine. So there's clearly a very big difference in the adjustment made. I have reached out to colleagues where some of the detection systems have been installed in similar conditions, and they verified that what they measure on structures are within this ballpark area, much closer than it is to the old method of calculation. So we do have confidence that this method mentioned in the standard is accurate enough to base any studies or calculation methods on. Now, once we've done a risk assessment and we know that our turbine will get struck 67 or 68 times per annum, it's very important for us to mitigate that risk as much as possible to ensure that we avoid unplanned maintenance and unplanned downtime. We know also now that it's not possible to avoid lightning strikes to a turbine. We know that the majority of lightning strikes would be upward lightning, and that we've done our risk assessment and we know what to expect. How many times per annum will my turbine be struck? Just as a side note, the lightning protection risk assessment standard for wind turbines states that you have to look at each turbine independently within a wind farm, unless they are within a radius of, I think, 300 to 500 meters of each other. Then they can be considered as one between the two, but otherwise you have to consider each turbine separately. Now, to mitigate the risk, we first again have to fall a little bit back on the standards to understand some of the terminology. Now, the lightning environment for wind turbines and the parameters associated with lightning current within wind turbines and dimensioning and analysis of the lightning protection system is mentioned in the ISE 62305 standard in part 1, and this is shown here, where lightning protection is made up of 4 levels. We have level 4 being the least amount of protection, and level 1 being the most amount of protection, or the best and highest level of protection. In a level 4, the system will start detecting or protecting from 16 kiloamps, and it will protect up to 100 kiloamps. In a level 1, it will start protecting from 3 kiloamps up to 200 kiloamps. So the band doesn't just increase on the higher side, it also gets closer to 0, so the band widens. We'll also look at smaller peak value strikes, so we don't miss small strikes. Now, it is a requirement from 61400 that lightning protection systems in wind turbines comply to lightning protection level 1. So they have to have the best lightning protection level, unless otherwise specified by a detailed risk assessment. Now, that's typically not something that you would see. Manufacturers would just manufacture it according to level 1. But if you don't know, please inquire this with the manufacturer on your wind farm as part of your wind farm design. Now, I mentioned that these lightning receptors are located along the blades connected to the down conductors, and there is a limit to what these lightning receptors can handle in terms of charge content after each and every lightning strike. Now, we mentioned at our characteristics slide that it's important to measure peak current and charge, because that is what affects these lightning receptors on the wind turbine blades. Now, according to ISC 61400, it's a testing requirement that lighting receptors must be able to withstand a single event of at least 300 coulombs of charge, or accumulatively be able to withstand 900 coulombs for multiple strokes. There would be similar suggestions for peak current, but it's typically for 200 kiloamps. As we said, we work with lighting level 1. Now, if you look at the pictures of these receptors, you can see this was 20 coulombs on one receptor, and it's still manageable. It's still easy to repair. This receptor is just removed and replaced. It's very quick, and the downtime is very limited. This is after another 20 coulomb strike to the same receptor. You can see again, still manageable, still easy to replace. When we go up to the limit of 300 coulombs, you can see that the damage is more around the outside of the receptor, and it starts damaging the blade, but this can still be repaired by only replacing a receptor. If we don't do this, and we don't monitor the amounts of lightning strikes and the amounts of charge onto those receptors, you can see on the right, this is an example of 4 300 coulomb strikes, which is an accumulated charge of 1,200 coulombs on a single receptor. And they are only able to withstand 900 coulombs cumulatively if they're manufactured according to standard. And you can see that the replacement becomes much more difficult. So this receptor is beyond replacement, and that means that you have to start cutting out portions of the blade and do repairs to the blade itself, and that creates longer downtimes and bigger unplanned maintenance. It's more expensive to repair as well. So the aim is to monitor the amounts of charge and lightning strikes on these receptors so that we are aware that the receptors have had multiple strikes, and we can go and replace the receptor rather than not knowing anything and then later just seeing massive amounts of the blade damaged, and that's when fires and things like that start to occur. Now, to measure this, we use advanced lighting detection and measurement systems nowadays. The lightning, as we mentioned, travels up from the base through the tower into the nacelle, out through the blade, and it goes up into the clouds with an upward strike. Now, the nacelle and the entire wind turbine, as we said, is manufactured according to lighting protection level 1. So there are very strong reinforced carbon brushes around bearings in the nacelle and across the yaw, and this is able to carry the lightning current to the point where it leaves the lighting protection system. And modern lighting detection systems are then installed inside. They could be installed around the base or the tower or around the shaft, and they measure the current traveling through this system out via the blade. And these detection systems have advanced so much that they can measure even the smallest amounts of current and charge, which was not possible to be picked up with older technology. And this makes the system very accurate. Now, this system is then adjusted to what your turbine is rated for. Now, the standard requirements, as we said, is 300 coulombs for a single event or 900 accumulated. But some manufacturers we see nowadays can go up to 5,000 coulombs accumulated charge. And again, if you start exceeding 5,000 coulombs, you will start having catastrophic damage. So it's important to measure that by means of a lightning detection system. And if we do this, we can apply preventative maintenance, and we reduce downtime and cost, and we also possibly avoid catastrophic failure in the case where we saw the turbine catching fire and those sort of catastrophic damages. The system, as I said, is typically installed inside the nacelle with a Rakovsky coil or CT around the shaft of the turbine, and it measures the current going through there. Some of these systems can be advanced even further, where you have units inside the blades where they have to be implemented during manufacturing, but they will even then tell you which blade was struck, and you can exactly know what blade to go and do maintenance on. It's also very important still to have surge protection in all electrical components within the turbine itself. If in some cases you see that the turbine blade does not cover the nacelle for a lighting protection level 1, It's a standard requirement to also have further lighting protection on the nacelle to protect this equipment on top of the nacelle as well. Now, if we briefly move on to the earth designs for wind turbines, the earth design or the earthing system, the grounding system, is incorporated into the foundation of the turbine itself. You can see here is a typical installation of a turbine foundation. Now, the foundation consists of rebar, reinforcing material, and concrete, and this forms the majority of the earthing system. Even through concrete, concrete actually extracts moisture from the swirl around it, and it becomes conductive. So concrete is also conductive in that sense. Now, the foundation material is used as the majority of the safety earthing, but in the case of lighting protection, we require that the reinforcing is welded at all these joints, welded very properly, or lashed quite extensively. And this is typically not done in industry. So what we do is we add lighting conductor within the foundation. You can see there the silver conductor there, and we clamp it to the rebar every 2 to 5 meters, creating these rings, and they basically just form bonding to make sure that the connection between all the rebar is very good and is able to withstand mechanical force during a lightning strike. Otherwise, if you don't do that, the lashing and things like that can go loose during a lightning strike, and it can cause mechanical damage and break off parts of the concrete and so on. Now, apart from that, you can also have ring conductors extending outside of the turbine that's connected within the turbine. This is required typically to control ground potential rise and avoid hazardous step and touch potentials, and it's more related to safety. However, it can also reduce the earthing resistance of the turbine earthing system as well. Now, this is just to elaborate again. You can see that the rebar is mostly used, and then these lighting conductors shown in red are inside the concrete connecting the rebar as well. This is a very basic representation, but you can see, for example, L1 is the red conductor, that's the lighting protection earthing conductor, and as indicated on the previous slide, you can use either galvanized steel or copper. There's a big misconception that only copper is allowed. You are still able to use galvanized conductor inside concrete as part of the foundation earthing system, and that saves a lot of cost as well. You can see on L4, this is connections for cross connections at the conductors, or for the conductors in the base, and L2 is just joining conductor. Inside the turbine, L3, we have something like this. We call these yellow points or fixed earth terminals, and these are connected to the reinforcing and the earthing system, and they're concealed when the concrete is poured, so they sit flush with the concrete on the inside, and you can attach anything like an earth bar and things like that to the earthing system directly for inside the turbine or inside buildings. And you can see some examples here of connections made from conductor to the reinforcing by using clamps, lighting protection tested clamps, and how this would be implemented. But again, the rings are mainly there to control ground potential rise and thus avoid hazardous step and touch voltages in and around the turbine base. Now, just a simple simulation for step and touch. This was done using XGS Lab. This is just to show you typically what it would look like, but it's still very similar to doing a normal earthing design for something like a substation. It's just required that you can simulate both above ground and underground structures, or within and outside concrete, add all those conductors and things like that as well. Now, it is a requirement to make sure that the earthing system is safe against step and touch during electrical faults, because this is also seen as a small substation. There are transformers located inside the base of the wind turbine, and in this case we did a step and touch calculation using XGS Lab software. We used the XGS FD or frequency domain model, and with that we can do both above ground and underground conductors. Now you can see here that we control the step and touch or the ground potential rise very nicely in the center portion, so there are not very big differences. If I have someone standing on the swirl surface and he steps or stands on two different potentials on this graph, there would be a voltage difference between his feet, and that voltage difference will cause current to flow between the feet, and that can cause electric shock. That's known as step voltage. Now the aim is to get this as flat as possible so that we don't have very large voltage differences, and you can see that it's pretty well achieved in this case, but you can increase this flat area of potential by adding more ring conductors to the system. As you can see here, we start then to control the ground potential rise, and we get that as flat as possible rather than having that cone that we saw in the first slides of voltage on the swirl surface, and that just makes it safer. You can also do lighting simulation at very high frequency using this XGS Lab software, and then you can also do calculation and simulation for lighting strikes to the turbine as well. Now, just to conclude the webinar, I discussed firstly that it's very important to understand how lighting is formed and why do we have different types of lighting strikes. The main focus in this case were upward lighting strikes, and this is because this forms the basis of all lighting strikes to wind turbines, or the majority of lighting strikes to wind turbines. It's also important to understand that it's not possible to avoid lighting strikes to wind turbines. IEC 61400 makes mention of lighting increasing within an area where wind farm is being erected, and the standard also gives you methods for determining the lighting risk to a turbine and the number of events to a turbine. The lighting protection system on turbines do, however, provide limited protection, and they have limited protection capabilities in terms of what they can handle through peak current and charge. And it's important to measure and monitor the lighting and charge current going through the wind turbine and the wind turbine blades and the lighting protection system and the receptors, so that those receptors are not overstressed and damaged catastrophically to the point where it damages big portions of the blade and causes fire and other catastrophic failures. It is also then important to consider the earth design, and to ensure that the earth design is safe against step and touch voltages by doing a safety earthing simulation using something like XGS Lab. But the earth termination system mainly consists of the foundation material, and you can add additional ring conductors if you are concerned with step and touch, or there's a requirement to drastically reduce the earthing resistance. Now, I hope you found this webinar very useful, very informative. As I mentioned, you're more than welcome to reach out to me, and I would be happy to answer any questions that you may have, or direct you to someone that can. Please let me know if there are any questions. Thank you again for joining, and enjoy the rest of your day. Goodbye.
All right, so that's the pre-recorded portion. I believe Yvonne is on. He's been answering questions. Yvonne, if you want to unmute yourself, I think you can answer any of the remaining questions if you want, and we'll typically leave this up for another minute or so after we don't have any questions, just to make sure people can still get theirs in.
Great, thanks Ted. Yes, so we received a couple of questions. I've been answering some of them through the chat itself. There are a few questions, a lot of them actually came through now at the end, so I'll try and scroll through as many as I possibly can and answer some of them that might be applicable to everyone, to maybe just understand. So one of the first questions was that, or what empirical data is available to show that turbines would be subjected to upward lighting strikes. The standard, the IEC 61400-24 standard, makes mention of this explicitly, that's what you can expect. And this is based on measurements that were done globally over a couple of years, but mainly focused on tall structures such as telecommunications, telecommunication towers or high-rise buildings. On wind turbines, there's been very limited data of measurement up to this point because it's still fairly new. But the upward strike phenomenon has been measured for many years now on tall structures, and that's where the data comes from. There was another question on should we now consider 61400 rather than the counterpart standard, which was 62305? And the answer is yes, definitely. So as you saw in the example, the number of lightning strikes calculated between the two was almost 10 times higher for the wind turbine scenario, and we have measured data to show that that's what you can expect on these tall structures. So definitely yes, when doing design or risk assessment for wind turbines, I would definitely suggest rather use the IEC 61400 standard as it is specifically suited for that. There was also a question on soil resistivity. So can the grounding grid resistance of the wind turbine be enough in lower rock, like rocky and crushed soil conditions to satisfy step and touch voltage? We've had cases where the soil resistivity is extremely high. It's usually the case. And to limit this, you can definitely do it. You can still get it safe against step and touch. It just depends on what your earthing system would look like. And you can add more rings for step and touch that typically would solve the issue. And you can have substation gravel around the turbine and dictate safety shoes as a requirement. So there was another question on why do lighting towers have like a mushroom or blunt time at the top. I'm not 100% sure what this is referring to, but the shape, I believe, does not have an effect on the capabilities. Now it works. If you maybe speak about a mushroom or something that looks like a globe on top of a rod, that's a technology known as an early stream emission device. That's typically banned by IEC standards due to many other reasons, but you're welcome to send me an email and I can send you some information on that as well. Ted, I think, can we take one more question maybe? Let's see, we've got like a minute left. Okay, there was another question on how does the lightning current go through the tower and through the bearing safely at the receptors. The IEC 61400 standard has a very specific testing requirements and testing methods. And the brush, there are these brush connectors on the bearings and rotating parts. And these brush connectors are very robust carbon connectors, and they are tested for lightning in lightning facilities to be able to withstand the lightning current passing through them so that they can safely do that. So it's a testing requirement from the manufacturer that the brushes at these bearings can handle the lightning current through the system. Okay, great. So I think the time is up. Okay, so any other questions that are left now in the chat, I will respond to them probably by email, or still if you stay in the chat, I will try to get through them as much as possible. But there were a lot of questions that came through at the end now.
Thank you very much, Yvonne. We'll go ahead and close this down. I want to thank everybody again for attending the webinar, and we hope to see you next time. Thank you.